expectation is a very important concept because other statistics courses typically deal with expectation, variance, covariance a lot, especially from a theoretical standpoint. So we've got to know what expectation is. First, expectation is defined for a random variable. For a constant, it would just be a constant value. From basic statistics, you should know what a weighted mean is, right? Enlighten me.
I can tell you how to do it, but definition.
Well, go ahead.
Well, usually it's like some kind of situation where you take a percent and you multiply it by the numbers and you find it.
So an example would be like your final course grade, like it's the mean between all your assignments, but like homework assignments are not weighted as high as like exams would be. So like she said, you would multiply it by the percent for like what the weight of each one is.
Exactly. So, by all means, and in Shay's case, it would, the denominator would always sum to 1. In your case, it may or may not sum to 1. So, if we go back and look at the definition of a weighted mean, I'll just call this W. Good. So, for instance, if we take Shay's example, this could be the grade that you make in homework, exam, the last exam, final exam, whatever. And WIs would be the corresponding percentages that are assigned for each of them. The denominator would add to 100%, correct? If it doesn't add to 100%, you're going to have a problem because it has to add to 100%. There are, yes, what? That's true, but I'm not that generous. So another example would be the number of credits that you take and the corresponding GPA value that you earn. For example, XI could be so a semester, you are taking a 3-credit course, a 4-credit one. Is there a 5-credit course?
There are a couple. Lab trails or something.
Okay, fine. Oh yeah, that's right. 4 plus 1, 5. And then the corresponding weight that we assign for each of them. Let's just say you made a C in that class, that would be 3. You made a B plus, that would be 3.7. I'm making this up. You made the other way around. You made an A, so that would be 4. You made another 3.5, C plus, whatever. And we want to find the weighted mean. So how would you do that? You simply multiply the weights with the X values. And you would divide it by the total number of weights that you have, or the sum of the weights, which in this case is simply the total number of credits that you have. 3 plus 4, 7, 12, 15. So what do we get? 9, approximately 15, 24, 44, 54, over 15, 3.8 something. You guys have a calculator. So for that particular semester where you took a 3 credit course, a 4, a 5, 3, your GPA for that particular semester would be 3.62. Now, how do we compute the average GPA or cumulative GPA at the end of your 4th year?
Take the weighted mean of all your semester GPAs.
So I'm simply going to take the average of all the semester GPAs, and that's going to give you your final cumulative GPA from FGCU when you graduate. Yes, with me. So now that I've asked that question, I am going to argue that the final cumulative GPA that I am going to compute is a form of weighted mean. In what way? Yes.
Or I have a question.
Oh, question.
Is it that you take the semesters and then just do a straight like add all the semesters and then divide by the
Yes.
number of semesters? So is it weighted just because you already took the weights into account each semester? So the weights are included in that 3.62. So when you do the final grade calculation.
Okay, so your explanation of, okay, this is a weighted mean. So when I average, it's just the average of weighted means. In that form, it is a weighted. Okay. I mean, semantically, that is correct. Alice, no. Did you have an answer?
No,
Okay,
I have a question, but.
what's your question?
No, it's not that. Okay.
So I was thinking, if you had a semester with like, say, 15 credit hours and you got some GPA, then you had some semester with, say, 9 credit hours and you get this GPA, and you add them together, isn't that going to skew towards, isn't that just going to make them evenly weighted when they should be weighted towards 15?
His question is actually approaching my answer. Yes.
You have to multiply the 15, well, in this case, 15 by 3.62, and then for him, you multiply 9 times where you GPA did for that semester, and then divide by 24 for all the credits paid.
Whole bunch of semesters, right? And these are all the weighted means for each semester. Agreed. At the end of your time at FGCU, we're simply going to take the average of all of them and give you a final GPA, right? Why? Because we've accounted for your credits per semester already. So your final GPA is this. Benton's question is, well, if I took more in one semester, fewer in the other, wouldn't that skew my average at the end? Absolutely, it will. But I'm not going to consider that, and I'm going to simply average them all together. My argument or my question is, if I call these yi, each of these values, yes, the final GPA that you get is in fact a weighted mean. I'll just call hi multiplied by yi divided by hi. Good.
What's it?
The weights. Instead of W, I've got H. So is it that they all have the same weight? That's it. They all have the same weight. In the sense, I'm treating them equally likely, right? They all have the same weight. So, but all means, when we say average, it is a weighted mean. An arithmetic mean, where we add a bunch of numbers, divide by the total, by definition, it is a weighted mean. That said, how do we extend this to probabilities and distributions? There is one distribution where we always have an equal weight, in the sense, equal probability. We have seen this before. Discrete random variable, which one is that? Uniform. We looked at a discrete uniform random variable, and there the probabilities were equally likely. So I could define if x is the expectation, excuse me, if x is a random variable, then the expectation of x would simply be equal to the sum over I, where I is all possible outcomes. You multiply each value, yes, that you could possibly have by its probability, pi. Good. So that is a weighted mean where you have pi would be wi, xi would be the values that you have. For instance, if I define x to be discrete uniform and and I would like to know the expectation of that. So if it is discrete uniform of 8, then what are the possible values for that? 8 possible values. What are the 8 possible values?
Okay.
Of course, you can do 0 through 7 also. I'm choosing 1 through 6 for a reason. If I asked you, well, what is the average of those numbers? What would you tell me? Oh, 4.5. Okay, let's see if we get that. So we've got to look at all possible values for x, every single value that I can think of. So 1 through 8, xi multiplied by pi. Yes. What is the probability of I? Oh, excuse me, the probability. It's a discrete uniform, so it will be 1/8, no matter what value you look at, it is going to be 1/8. Correct? I could pull 1/8 out. Which would give me 1/8 multiplied by sum I equals 1 to 8 xi, which in this case you are adding n integers from 1 through 8. So what would that sum equal to? Did we take finite math? Discrete math? Okay, the sum of n natural numbers is n times n plus 1 over 2. So n is 8, so 8 times 8 plus 1 over 2. 8's go away, 9 over 2, 4.
Was that sum of n natural numbers is n times n plus 1 over 2?
Yes.
Okay.
So, do you believe that in practice this would be the case for every scenario? No, because we have seen other cases. We have seen binomial we've seen hypergeometric, we will see geometric and so on, and a bunch of others. So this is the simplest trivial case. But since we have other cases, a generalized version of representing this would be for all xi in omega. In other words, we are taking all outcomes that are in the sample space. We're going to take the outcome and multiply it by its probability. Good? Okay. Because I could look at this graph and come up with a table. Yes. What are the possible outcomes in the sample space? 1 through 6. Is that this great distribution that you see uniform? No, clearly not, because they don't have equal probabilities. But just by the looks of it, if I asked you, well, where would the average be? What would you tell me? 1 or 2. I'm going to say probably is going to be about 1.7. Why not? Let's just make this stuff up. Why is that, Nathan?
Because it's you.
So majority of the probability is right over here. So, so what we're going to have is numbers, more numbers from here than the other values for 5 and 6. So if I want to find the expectation, I will simply take each outcome that is possible, multiply it by the corresponding probabilities, sum them all together. You can do that and tell me what you get. This is 0.08, 0.08, 0.1, 0.2, 0.2, and 0.34. It should add to 1 now. So change that 0.34 to 0.54 to 0.34. So each value multiplied by its probability. So 1 has a probability of 0.34. 0.2 times 2, 0.2 times 3, plus 0.1 times 4, 0.08 times 5, 0.08 times 6. Point 0.62 could definitely not be an answer because it's over here. If that was the case, my life would be meaningless. Everything I've learned must be wrong. So 2.62, it sort of makes sense because the majority of values are over here. So somewhere over here is where we would expect the average to be. Now, when we talk about expectation of x, expectation of x is actually a parameter. And it is a theoretical mean. So for any scenario, the moment I say expectation, when I do derivations in mathematical statistics, whatever I am deriving, it is for the theoretical case. Now, in practice, we're not going to get the exact same value, but we will get a value close to 2.62. The reason why we call this a parameter or theoretical mean is because that is a known distribution. So since the distribution is known, which is this, if I tell you that this is a true distribution for some process, then this value is the truth. This would be the theoretical mean or the parameter. But if you follow the process, that's defined by this distribution, you collected a sample, whatever sample that you collect will have a mean, but that mean is not going to be close to 2.62. If it is completely random, sure, but if there was some issue, we will get closer to 2.62, but not the exact 2.62. So most common mistake that people make is calling expectation of X to be the sample mean that you find in your calculator. No, this is a theoretical mean. This parameter, whatever you get from a sample is the sample mean. All of mathematical statistics, derivations, theory, etc., 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 they're all based on expectations, theoretical parameters. So here is a problem. So the probability that an accident would happen at an intersection at night is 0.82. Four cars pass through the intersection on a random July night. If X is the number of cars out of the 4 that end up in an accident, find the PMF of X. As I went around, some took the counting approach and then put the probability, used multiplication rule, used addition rule, got the answer. It's all nice, but one of the important things in statistics on top of other important things is to identify the distribution for a given scenario. So if you identify the scenario, then you can easily come up with the probability, because people have come up with all kinds of distributions that we can use in practice. So what would the distribution of X be? X. It is binomial. And what are its parameters? 4 and 0.82. Now that I've identified the scenario, I can proceed with the PMF easily, because I told you it's in your calculator. We could use binomial PDF to get the answer, or PMF. They call it PDF, but it's PMF. How did I identify that this is binomial? Well, I have 4 cars. The 4 cars are independent of each other, and the probability that an accident would happen at the intersection is 0.82, success being an accident happening. So we have 2 possibilities at each trial for independent trials. Either you get into an accident or there is no accident. So n independent trials, a probability of success, which implies you get into an accident. So that scenario can be modeled using a binomial NP. You can't forget the parameters. So you don't have to write this PMF out, but I'm doing it for a reason. What are the possible values for X? 0, 1, 2, 3, 4. And what are the probability?
For 0.0010.
Okay.
0.0191.
Okay.
0.1307.
Okay.
0.3969.
Okay.
and 0.4521.
If you graph it, would you get a skewed distribution? Is it skewed to the right or is it skewed to the left? It's skewed to the left. So majority of the observations lie on the right hand side, a few lie on the left hand side, it's skewed to the left. And if I asked you, well, on average, how many accidents do you expect to happen?
Like three.
About 3 accidents, right? Why?
I think it's-
What is your name? Nick, not that I'll remember, but. Nick, the data is skewed, but in what way?
So it's concentrated around 3 and 4.
Concentrated around 3 and 4. So you have greater probabilities here, but 2's got some probability too. So it has to be somewhere here. If we use the formula,
What are the cars getting in an accident with?
Huh?
What are the cars getting in an accident?
Something. some kind of accident.
With a spill.
You know, they can, you know, to blind intersection, you know, top row, something happens. And that's-
So the 0.2 is the probability that when a car drives through the intersection, it has an accident.
Point
Is that what that
82,
0.2 is?
0.82 is probability that the car will end up in an accident.
And that's just one car.
Yeah, one car. So, well, if you write this out, 0 times 0.00101, the next outcome 0.0191. 2 times 0.1307. 3 times 0.3969. 4 times 0.4521. If you put that in the calculator, what do you get? Huh?
3.28.
3.28.
Only there was a computer.
Patience then. So there is a reason why I'm doing all this. So we did this, we have 3, great. What if you have a scenario where you have more than 4 cars and you look at a busy intersection and, you know, people constantly get into accidents at that intersection and 57 cars go through that intersection. Do you really want to do this? No, there has to be a quicker way. So if you know the probability of success, which you can get it from a sample, then you associate that with the scenario, and in your head you can automatically come up with the mean. Once you get the mean in your head, you can easily get estimates as to where the probability will lie and if it is going to be skewed to the left or right. There is only one way where this would be symmetric, and what value would that be? Huh? If P is 0.5, that is the only time when you get a symmetric PMF. In all other cases, it is going to be skewed. Less than 0.5, it will be right skewed. More than 0.5, it will be left skewed. That said, what is the easy way? So 0 through n, and x is going to take all possible values from 0 through n. we are going to multiply it by the probability of x is equal to xi. But we know that we have a closed form expression for a binomial EMF. What is that? Closed form expression in the sense you have a formula. What is that formula? You can look at your notes. Okay. We know what n is in this case, but I'll write it later. N choose k. Here is k. Here is n minus k. Q is just the probability of failure. I keep using Q instead of 1 minus Q because that's very formal. But for this case, we have n to the 4, p is 0.82, and q is 0.18. We shouldn't be plugging stuff in. That will defeat the purpose because if you plug stuff in, we're going back to what we did already. So we're trying to derive a formula. In terms of factorials, what is n choose k? Okay. Good. I'd like to simplify now. So I could write k factorial as k minus 1 factorial multiplied by k.
Excuse me, question. Would it be appropriate to write it as k equals 0 because not all binomial distributions are going to have constant? I'm thinking something.
The case will get cancelled. And you end up with this formula. And there is a different mindset on how a statistician would look at this and approach the problem, and how a mathematician would look at this and approach the problem. So a math person, purely math, would go for some sort of combinatorial arguments, use combinatorics, sum theorem to simplify this and, come up with a solution. A statistician, on the other hand, will try their best to express this in terms of another distribution. In other words, is there an equivalent distribution? If I know that equivalent distribution, so what holds true for this, or excuse me, what holds true for that distribution will also work for this one. So I'm going to try my best to rewrite this in some form so it matches one of the distributions that we already know. To do that, I am going to write n factorial as n minus 1 factorial multiplied by n. So if you ever plan to become, a statistician and work on theoretical stuff, you cannot forget this piece of writing one distribution in terms of another, because that's how we simplify a lot of problems, both here as well as in Bayesian statistics. So that n is a constant. Do we agree? So I could pull that out of the sum. I'll have n minus 1 factorial divided by k minus 1 factorial, n minus k factorial, p raised k, q raised n minus k.
I do have one quick question. Earlier on, when you divided by k, should you pull out the case where k equals 0 first because you can't divide by 0?
I'll do it at the end. Yeah, I'm about to change.
Why is it negative n? It's not up to the snare.
So I guess this is a good time. So since I have k minus 1 factorial, I cannot start at 0, right? So I will change the sum to, or sum from k equals 1 to n. And I'm going to do a trick. Inside n minus k, I'm going to add 1, subtract 1. Did I do anything wrong algebraically? No. P raised k. Do the same with n minus k. I'm going to add 1, subtract 1. If it's at 0, you will have negative 1 factorial.
That's true. Although, isn't, I mean, that's just factorial right now, like the game function.
Yeah,
So like negative 1 factorial doesn't exist.
you can evaluate it using the gamma function, but in the discrete case, I'm not considering. And also, I don't want k to be negative 1, because in a practical sense, could you have negative 1 number of successes? No, right? Intuitively, also, I don't want to put that negative 1. And the support of gamma function is from 0 to positive infinity. So you can't put a negative 1. So I can move that negative 1 and combine it with n. So I will have n minus 1. If I pull a negative out of those two terms, I will have k minus 1. Good. So all I'm doing is rearranging the terms so that I get n minus 1, k minus 1, and factorial. P raised k. Do the same thing. I could write this as n minus 1 minus k minus 1. Suppose I make a substitution that m is equal to k minus 1. then this form would reduce to sum. Well, when k is 0, it is going to go to, excuse me, when k is 1, what is m? 0. When k is n, what is m? These are easy questions, Peter.
N minus 1.
N minus 1. N minus 1 factorial, n factorial. No, wrong substitution. N minus 1 factorial. K minus 1 factorial is n factorial. N minus 1 minus m factorial multiplied by p raised n plus 1. Yes? Multiplied by q raised n minus 1 minus n. With me so far? All I did thus far is algebraic manipulation. Have p raised n plus 1, so it's p raised n times p. So I could pull a p out. So I would have n times p. M equals 0 to n minus 1. N minus 1 factorial divided by m factorial multiplied by n minus 1 factorial. P raised n, q raised n minus 1. I could write this expression in terms of the combination function that we know, binomial coefficient. So m equals 0 to n minus 1. I could write this as n minus 1 choose m. Do you agree? N minus 1 choose m is simply n minus 1 factorial divided by n factorial multiplied by n minus 1 minus m factorial. P raised m, q raised n minus 1 minus m. What?
Yeah. It's going from,
I'm trying to rewrite the expression that I had in terms of another distribution.
Yeah.
In doing so, I did algebraic manipulation by adding and subtracting 1 that resulted in this. Got n minus 1. Did you write it all down?
I've been trying to. Yes, I
So
figured it out.
that's where you get n minus 1. You add and subtract 1 earlier, and you do a bit of manipulation. You end up getting n minus 1. And why am I doing all this? I am trying to write that sum in terms of another distribution. Same thing. Can be applied to continuous distributions. For instance, gamma distribution, the support is 0 to infinity. So as long as you have another sample that resembles like a gamma, and in other words, it is right skewed, and its support is 0 to infinity, then you can rewrite whatever expression that you have in terms of the gamma. Gamma is a continuous distribution, which we will talk about when we get to continuous. Ultimately, at this point, I have successfully wrote that original sum in the form of another distribution. Again, if a pyramid mathematician would take a combinatorial approach using a theorem, whatnot, the approach that statistician would take is always try to rewrite it in terms of another distribution. I am going to argue that that is a PMF of a discrete random variable. What is a discrete random variable? Caleb, right? Very close. So Andrew says that this is binomial. Okay. A binomial has two parameters. What are the two parameters? N and P. In this problem, what are those? N minus 1 and P. So, in other words, we kind of see that this is the probability map, or we not kind of see, we see that this is the PMF of a binomial distribution. The parameters of this binomial are n minus 1 and p. If it is binomial n minus 1 comma p, the support has to be 0, 1, 2, all the way up to n minus 1 comma p. N minus 1. A regular binomial, if it is n comma p, 0, 1, 2, all the way up to n. Here, it's n minus 1 comma p, so 0, 1, 2, all the way up to n minus 1. Great. So this is a PMF of a random variable that has a binomial n minus 1 comma p PMF. So if we sum a PMF over its entire support, what would we get? One, the sum, earlier, well, that pen's gone. Earlier, when I drew that distribution, Benson said it can't be a distribution because it doesn't add to 1, right? This is a proper PMF. So if I add it over its entire support, that would reduce to 1. So expectation of x is n times p. So the theoretical mean of a binomial distribution with parameters n and p are, or is, simply n times p. Yes?
I was wondering why 4 times 0.82 was 3.28.
Now you know. Right? So, if we have a sample and if we know that it follows a binomial distribution, we can immediately find, its expectation. So going back to our example, n equals 4, p equals 0.82. What is n times p? 4 times 0.82, which is 3.28. Yes? So we did all that work trying to come up with the table, the formula, the table to get that expectation to be 3.28. But it is a lengthy derivation, but the advantage of this derivation is once we are done, we have a nice little formula. So if I could model a scenario as a binomial, I can immediately recognize its PMF and its expectation. Later on, when we do variance, the same process. So if I recognize that it is going to be 3.28, I will know that it has to have probabilities, heavy probabilities around 3, and smaller values for probabilities around 0, 1, and 0 and 1, because we only have 2, 3, 4. If you go back and look at the PMF, you had fewer probabilities or values that were very small for 0 and 1, and higher probabilities happened for 2, 3, and 4. Does that make sense? So the theoretical mean of expectation or expectation for a binomial is simply n times p.